For this video, I'm going to have you complete integration by parts on this example right here. Then we're going to focus the rest of this lesson on something called the tabular method, which is just another organizational tool to use when you're using integration by parts. So I'm going to show you how that works. But right now, go ahead and pause the video and complete integration by parts for this example. And I'm going to warn you, on this example, you actually are going to have to use integration by parts twice. So you have been warned. All right, so once you get to this step right here, you're going to have to use integration by parts again. So check and make sure you're right, and then pause the video and keep working through. All right, so here is our final answer. Couple things to note. Remember that when you integrate sine, you get negative cosine. That's why this became a positive. And that I reversed the chain rule here. So I multiplied by 2 in blue and then multiplied by 1/2 in blue so that I could integrate without having to use u substitution, especially since I already defined u, v, w, and y. I don't think I want to define another variable in this problem. So based on what we've learned so far, this is the only way that we know how to integrate a problem like this. And it is taking up a lot of space and a lot of math and leaving room for many, many places to make errors. And there is another way that we can integrate using integration by parts still, and it's called the tabular method. We aren't going to go through the proof of why the tabular method works. It's just not relevant right now. You can look it up if you really want to. I'll help you find a good proof. But we're just going to go through the process of doing it because it really is just another way to organize in a table form what we're doing for integration by parts. So when you are doing this, you're going to always start with a sign column in your table on the far left, and that's always going to alternate starting with positive. So it will always start with positive. It will alternate until you no longer need any more signs. You're going to start the middle column with whatever you are defining u to be. So you're going to start with u. In this case, u is x squared. And then in the far right column, you're going to start with whatever you're defining dv to be. And you don't need to write dx. So we defined dv on this problem to be sine of 2x. All right, so to recap, signs in the table starting positive, alternating positive, negative, positive, negative. U, what you're defining to be u, which is the same thing that we did on the left over here, is in the middle column, and what you're defining dv to be without the dx, you just don't need it, it's not necessary, is going to be in the far right column. In the middle column, you're just going to take the derivative, and you're going to keep taking the derivative until you get to 0. So the derivative of x squared is 2x, the derivative of 2x is 2, the derivative of 2 is 0, that's when I'm going to stop. You are then going to integrate sine of 2x for the same number of times that you had to differentiate your u value. So if I take the derivative of sine of 2x, I get negative 1/2 cosine of 2x. If I take the derivative of if I integrate negative 1/2 cosine 2x, I get negative 1/4 sine of 2x. If I integrate negative 1/4 sine of 2x, I get positive 1/8 cosine of 2x. So that's how you set up the table. And now the tabular method only works when your u value is converging to 0, when eventually you're going to get that u is 0. Otherwise, this method isn't going to work, and you're going to have to do integration by parts the long way. So now that we have done this, you are going to ignore the first dv value, and you're going to take everything here and multiply it together. So that's going to give me x squared times negative 1/2 cosine of 2x. And then you're going to do the same thing with the next part, minus, and I'm running out of space, so I'm going to just go under minus 2x times negative 1/4 sine of 2x plus the last part, plus 2 times 1/8 cosine of 2x. And if we simplify this, we're going to get, spoilers, since you already did this in the warm-up, we're going to get this exact same thing, but let's just verify that. This is going to give me the red portion, negative x squared over 2 cosine of 2x confirmed over here, minus 2x times negative 1/4 is going to give me positive x over 2 times sine of 2x. Then I have 2 times positive 1/8. That's going to give me plus 1/4 cosine of 2x. And then I do need to add a constant of integration at the end here. So this is not written very nicely, but it is in fact this same answer up here. So the tabular method: set up your signs, set up your u and take the derivative until you get to 0. Set up your dv and integrate the same number of times that you had to take the derivative. Then you're going to ignore your first dv and you're going to make those little circles to set up the table. Let's look at another example, and I'm going to erase what I just did after this to give us a little bit more space. Now, some of you are probably thinking, do I have to do this problem using the tabular method? Couldn't I just integrate using integration by parts like we did in the first half of the notes for 6.3? You absolutely can. No one is ever going to say, set this up and integrate it using the tabular method. You're in calculus. It's just going to say, evaluate this integral. However, comparing the work from what we just did in the warm-up to setting it up in the tabular method, it is going to be a time saver. So I definitely prefer it on problems that I can use it. So I'm going to go ahead and set up the sign chart, alternating signs, starting with plus. I don't know how many I'm going to need, so I'm going to start with 4. I can always add more if I need more. I'm going to have my u and my du here. I'm going to have my dv and my v here. So in this case, u is obviously going to be x to the third. When I differentiate that, I get 3x squared. Then I get 6x. Then I get 6. Oops, I am going to need one more. Then I get 0. I need one more plus sign there. For my dv, that leaves me with e to the 4x dx. When I integrate that, I get 1/4 e to the 4x. When I integrate that, I get 1/16 e to the 4x. When I integrate that, I get 1/64 e to the 4x. When I integrate that, I get 1/256 e to the 4x. Now I'm going to make my little circles. Sound effects are always helpful. This is going to give me x to the third over 4 e to the 4x minus 3x squared over 16 e to the 4x plus 6x over 64 e to the 4x minus 6/256 e to the 4x plus c. Don't forget your constant of integration. There is no reason for you to simplify any of those fractions. Again, you're just putting yourself at risk for making an algebra mistake that will cost you a calculus point. So you can go ahead and leave it like that. Let's look at some more examples. All right, for the next 6 problems, I encourage you to decide at the beginning, can you use the tabular method? If you can, just for this section of notes, I challenge you to use it. After you finish this section of notes, you can say, I hate this method and I never want to use it again. It's totally up to you, but I recommend that you use it if you can on this and then you make your decision after that. It will not work on all methods. Remember, if your u value when you differentiate it is not going to converge to be 0 at some point, then you can't use this method. So before you begin each problem, which I'm telling you, you're going to have to use integration by parts on each of these 6 problems to save you some time here, decide if you can use the tabular method or not. So go ahead and pause the video, work through these first 3, and then unpause the video and see how you did. So here's the tabular setup on number 1. And then we're going to group. So this is going to give me x to the third sine of x minus 3x squared times negative cosine. So plus 3x squared cosine of x plus 6x times negative sine of x. So minus 6x sine of x minus 6 cosine x plus c. Go ahead and set up the table on number 2, if that's a possible method here, and work through number 2. So here's the setup for number 2. And then you can go ahead. I'm going to go down under this box because since I didn't save myself enough room, we're going to go number 2 right here. So 2/5, I can read my own handwriting, 2/5 x squared times x plus 1 to the 5/2 minus 2x times 4, so 8x/35 times x plus 1 to the 7/2 plus 2 times 8, so plus 16/815 times x plus 1 to the 9/2 plus c. Go ahead and set up the table if possible on number 3. Either way, use integration by parts to evaluate number 3. So here's our table. The first term in our answer is going to be x tangent x minus 1 times negative natural log, so plus natural log of the absolute value of cosine of x plus c. All right, 3 more problems. Let's take a look. So for all 3 of these last remaining problems, you cannot use the tabular method because neither function has a derivative that's converging to 0. Or on number 5, the problem is that we have to define u to be arcsecant because we don't know how to integrate arcsecant. So I'm actually going to encourage you to work on 5 and 6 first, and then come back and we're going to do number 4 together. Number 4 looks like the easiest of these 3, but it is in fact the trickiest. So pause the video and go ahead and work on 5 and 6. All right, so here's number 5. You can see u and dv defined, the integral set up. I can eliminate this x, one of the x's from x squared with absolute value of x, since we have this domain restriction at the beginning anyways, that x is greater than 0. Then I have to use u substitution, regular u substitution, to evaluate that integral in red. And I did that off to the side in green. Let w equal x squared minus 1. You can see that substitution happening to get this 1/4 here. That's coming from this negative 1/2 and this 2 in the denominator. This 2 is coming from integrating u to the negative 1/2 power. That becomes u to the 1/2 power divided by 1/2, which means multiplying by 2. So that's how that came about. Clearly, I do not have enough space to work through these other 2 problems here. So I'm going to go ahead and write them fresh on a new slide. But why don't you start trying to work through number 6? Again, we're going to do number 4 last. All right. On number 6, you may have needed to show a little bit more work than I showed, but you can let u equal x e to the 2x, which means you need to use the product rule to find du. That means that dv is 2x plus 1 quantity to the negative 2nd power, and you're going to integrate that to find v, which is negative 1/2 times the quantity 2x plus 1 to the negative 1st power. So you're going to set up your ultraviolet voodoo, uv minus the integral of v du. I factored out the negative 1/2, so that's where plus 1/2 came from. And in the numerator of that integral, I factored out the greatest common factor, e to the 2x, so that then my 2x plus 1's divided to be 1. To integrate e to the 2x, I put a 2 here, and I put another 1/2 here, and that's where this 1/4 came from. And that gets us to our final answer. Again, until you get really comfortable reversing the chain rule, it's possible you might have to show a few more steps than I showed here. All right, let's look back at number 4. I want you to define u to be sine of x and dv to be e to the x dx, and then I want you to set up the integral. So once you do integration by parts one time on this problem, you may start to notice it seems like this is never going to converge to anything. It's never going to go in a way that helps me, but I'm actually going to encourage you to do integration by parts one more time and see what happens. So this time, doing it with this integral in blue here, you're going to let u equal cosine of x, and you can't use u, so let's let w equal cosine of x, and I encourage you to do integration by parts again and see what happens. So when you set it up, make sure you're distributing this negative sign appropriately here. Part of you is probably saying, Judson, what are you doing to me here? I'm back to where I started. I still have this integral that even if I try to do this again, I'm just creating this vicious cycle. And that is what I want you to notice. You do have this integral that you started with, right? That looks exactly the same as this over here, which means that we can actually combine like terms, right? I could add, well, not combine like terms. I could add the integral of e to the x sine of x dx to both sides, which means I would have 2 times the integral of e to the x sine of x dx equals e to the x sine of x minus e to the x cosine of x, which then means if my ultimate goal was to solve for this thing that I have in black, to solve, I can just divide both sides by 2. So the integral of e to the x sine of x dx, sorry, my pen is starting to just not work today, is, I'm going to just put 1/2 times e to the x sine of x minus 1/2 e to the x cosine of x. And that gets us to our answer. And since we didn't actually integrate, but at some point we did integrate, we are going to have a plus c on here. And this should feel a little bit weird. We did integration by parts, but we never actually evaluated a final integral. We used basic algebra, some pretty complicated looking like terms that we're combining when we add on both sides, but it is getting us there to this final answer. So you will see situations like this occur only when you basically have 2 functions that are just going to keep repeating themselves. You're alternating back and forth, like in this case, sine of x, and then combining that with e to the x. So main points for these notes: summarizing and getting more practice with integration by parts, but also learning the tabular method, which works when our derivative is eventually going to 0 for u. You should be able to identify when you can use the tabular method, even though you're never going to be asked to. It'll just save you some time and effort. You should also make sure that you're just getting more and more comfortable integrating using integration by parts. Looking forward to supporting you with this in class. Thanks for listening.